Pre-calculus, horizontal asymptotes continued for the next few minutes. We just finished first and second period class, and these were the notes on finding horizontal asymptotes. You see our learning target for today is students will write the equation of the horizontal asymptote given a rational function, right? So this whole unit is on functions that are fractions. So if you have other functions, like say y equals cosine of x, that's not a rational function. Maybe it has a horizontal asymptote, maybe it doesn't, right? There's different rules that apply. But these are the three rules that apply to rational functions. And with a rational function, you're comparing what the numerator of the function is doing to the denominator of the function, right? You're comparing the rates at which they change. And so when the numerator changes less than the denominator does, the horizontal asymptote is 0, right? And so we see three examples here. 1 over x. Notice the numerator is not changing at all. The first example. 1,000 over x minus 5. The numerator is not changing at all. So I picked two different numerators. One's really big and one's really small. But still, they're not changing. If you look at the denominator is changing, right? And 1 over x, the denominator goes from a 1 to a 2 to a 10 to a billion to infinity plus 1, right? And so as the denominator gets larger and larger and larger, this first example was basically, the pizza we were talking about. If you cut a pizza into more and more and more slices, okay, each slice gets smaller and smaller and smaller. So the horizontal asymptote would be 0. Right? If you cut a pizza into 2 pieces, you each get a half, you and your friend. But if you cut into 10 pieces, it becomes a tenth. If you cut into 100 pieces, it becomes 0.01. Cut it into 10,000 pieces, it's 0.00001. So it's smaller and smaller and smaller amount, right? So the overall number gets smaller as the denominator grows faster than the numerator. This last example over here, notice the numerator varies. The numerator is going to change. The numerator becomes a 1, the numerator becomes a 2, the numerator becomes a 3, and so does the x in the denominator. But in the denominator, you're squaring it. So 1 squared, 1. 2 squared is 4. So the denominator is growing larger faster. So when the degree of the numerator is less than the degree of the denominator, okay, the degree is, again, the highest power of the polynomial. It's the highest power of the numerator and the highest power of the denominator. So when the degree of the numerator is less than the degree of the denominator, your asymptote, horizontal asymptote, will be y equals 0. It will be the x-axis every time, okay? If the degree of the numerator is equal to the degree of the denominator, when they are equal, the horizontal asymptote is a ratio of their coefficients. Okay, so you'll notice x plus 2 over x plus 3. They both have the same degree, right? They both grow at a rate of 1 power. And 1 divided by 1 makes 1 because their coefficients reduce, right? The coefficients of 1 over 1. If I have 3x squared plus 7 over 1x squared, this minus 2x plus 8, that doesn't really matter. The plus 7 doesn't really matter. Okay, that obviously they affect the graph. It changes the steepness or the stretch of the graph. But the horizontal asymptote is going to be a ratio of 3 over 1 because their degrees are the same. Okay, 7 over 13 is the horizontal asymptote. And that's when they're equal, right? So what if the degrees become the opposite? The numerator grows faster than the denominator. So this was this last example. This is when you have no horizontal asymptote, okay? This is when your graph will go up towards infinity, or it'll go down to negative infinity. Down, up. Down. Anyway, so what I thought might be helpful is to actually see some graphs. Maybe I should get me out of here. You don't really need me here. I might be in the way. Goodbye, Mr. Quirk. Just get out of here. If I have 5 over x minus 1, right? Think about what's happening here is the numerator is not changing. The denominator is going to grow when the numerator doesn't. So this is an example of the degree of the numerator is less than the degree of the denominator. And when the degree of the numerator is less than the degree of the denominator, we expect the horizontal asymptote to be where? That's right. Good job. the x-axis, or y equals 0. You notice this graph is flattening out towards y equals 0, just like the one we did in class. Okay. Where is its vertical asymptote? So one of the things you might not know about the graphing calculator is if you hit trace, that'll show you your equation at the top. You can also trace numbers. Like I can trace 9. See, when x is 9, y is 0.625. Right, so it's getting smaller. I can trace 10 because 10 is the last, but 10 is the last number in my window. So notice the numbers got smaller, 0.55. If I trace 11, it'll say error, because 11 is outside of my window. Right, you have to change your window. So let's just go to 1. Notice when x is 1, y is nothing. There's no answer. Because remember, this is the value that makes the denominator 0. When the denominator is 0, you get undefined, right? So undefined means vertical asymptote. So there's a vertical asymptote at x equals 1, horizontal asymptote at y equals 0. Okay, so we change this equation a little bit. Like, let's make this 5 x sorry, interruptions. 5x squared, right? So notice with 5x squared, 5 over x squared minus 1. What's happening now, right? Notice the denominator is still growing faster than the numerator, right? The denominator's bigger than the numerator. So the numerator's less than the denominator. That's probably how I should stick to saying it, right? If I graph this, I should still expect to see the horizontal asymptote at 0, which it is, right? Notice this graph is flattening out to 0. But by squaring the denominator, we see a whole nother creature occur, because notice now there are 2 vertical asymptotes, because x squared minus 1 would equal 0 at -1 and +1. If I try tracing 1, it'll say y equals nothing, because there's a vertical asymptote at x equals 1, right? At -1, there's a vertical asymptote at -1. It's 2 vertical asymptotes, okay? But the horizontal asymptote is still at 0, y equals 0. Okay, if I were to change this denominator to a +1, this would change it up a little, wouldn't it? Because at what point now does x equal 0? Or sorry, what point does the denominator equal 0? Does x squared plus 1 equal 0? No, it never does. We had this show up in our homework. We already talked about this in class today. So if I graph this one, notice the horizontal asymptote is still 0, but there is no vertical asymptote, right? There isn't a vertical asymptote anymore. Okay, cool. So if I go to y equals, and so we're just affecting vertical asymptotes and horizontal asymptotes. If I were to put an x in here, this is something that's pretty exciting, worth mentioning. Right, 5x divided by x squared plus 1. So when does the denominator equal 0? Never. So there is no vertical asymptote, right? But notice the degree of the top is still less than the degree of the bottom, right? The horizontal asymptote should still be 0. The horizontal asymptote should still be 0. And look, there is a horizontal asymptote at 0. The y-axis is still a horizontal asymptote. The graph is going to get closer and closer and closer to 0. And how can I tell? Another thing I can do is go to the table, right? So again, we haven't done a lot of calculator work at all in this class. I don't know how much you know about the calculator. You go to y equals, you type in the equation, you hit graph, you see a picture, and then you've got second table to see the table. Notice as x gets bigger and bigger and bigger, y is getting smaller and smaller and smaller and smaller, right? So if I go past 10, 0.4, 0.3, 0.2, right, all the way out to 0.1, so it is getting smaller and smaller. It's going to keep getting closer and closer and closer to 0. It comes to a point where, oh man, 0.062, that's as far as I want to go. It comes to a point where it just becomes 0.0000001, right? What I wanted to mention about this graph is, notice this graph is a weird example where it does cross the asymptote. So we have this kind of definition in our head about the asymptote is like a boundary line the graph never crosses. And that is definitely true for a vertical asymptote. If the vertical asymptote exists, then there isn't an x value where it works. But it turns out for this particular equation, right, this was 5x over x squared plus 1. It does equal 0 at 0. This function does cross the y equals 0 asymptote, but notice it's crossing it in like the middle of the function. So this is a time where the asymptote is showing up at the end behavior, right? As x gets bigger and bigger and bigger, the asymptote is working, or as x gets smaller and smaller and smaller, the asymptote is there. But it does cross it in the middle, and that's okay. So sometimes a horizontal asymptote gets breached, if that makes sense. It gets crossed. This graph is actually what's called a serpentine. Whenever you have an x over an x squared plus a number, this is called a serpentine. It's kind of like an elongated S. It makes me think of Cars, like when Lightning McQueen is like serpentine, serpentine, because like he crashes into the town, and like I think it's when the big fountain of the old like Henry Ford car gets like stuck to the wire that's that's like a telephone wire. I don't even remember anymore. And he's dragging it all over town, and it's like tearing up the road, and he's like trying to dodge it, and he's like serpentine, serpentine, but it's like stuck to him. So this is your serpentine. It's like zigging and zagging, right? It's like, whoa, we're over here, dude. Woo, we're cutting back this way. No, dude, whoa, we're going over there. So it's like serpentine. Anyway, maybe one or two more. What if I change this? And something else you might not know about a graphing calculator. If you put your cursor where you would like to put something, you can hit second and insert an expression. That saves you from having to retype the whole thing. Notice now my degree on top is equal to the degree on the bottom, right? So when the degrees are equal, I should finally see my horizontal asymptote moving from the x-axis, right? It should not be y equals 0, but it should be y equals what? Yes, 5, right? So if I graph this one, notice the graph is now plateauing or flattening out at y equals 5, right? If I were to even put in the equation y equals 5, right? So the equation of the asymptote line is y equals 5, that horizontal line. And that blue curve, it will never, 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 never touch 5. It will never get all the way to 5. Okay? And if I were to go back to my table, right, notice at 83, it's at 4.9993. Right? If I just keep going down, 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 down. So this graph is getting closer and 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 closer to 5. The y1, remember, is my curve. It's never going to get to 5. Even if I were to jump like way out, the horizontal asymptote is 5. If I were to change this 5 to a 6, right? Get rid of this, delete. It would now be 6. So notice it's up at 6 now. 1, 2, 3, 4, 5, 6 is up here. If I were to change the horizontal asymptote to, let's see, insert a negative, and let's change the 6 to a different number. Yeah, I don't know, make it 2. Okay, what should the horizontal asymptote be now? Remember, it's a ratio of their coefficients. The coefficient is -2 on top, +1 on the bottom. And what's -2 divided by +1? You're right, -2. So notice the graph flipped over, but the horizontal asymptote is -2. Okay, so when the degree on top, square, matches the degree on the bottom, a square, the ratio of their coefficients is the horizontal asymptote. And that would be true if I change this second power to a third power. It's going to be a different looking graph. I don't even know what this is going to look like, honestly. Oh, that's crazy funky. So you think about what's happening now. Is it possible for the denominator to equal 0? Yes. If you plug in -1, what is -1 times -1 times -1? That is -1, right? -1 cubed is -1 plus 1 makes 0. So at x equals -1, if I were to trace -1, it'll say y equals nothing, right? There's a blank. There is a vertical asymptote at -1. That's the vertical asymptote. But notice the horizontal asymptote, right? Y equals -2, right? So the red curve, it looks like it's bleeding into the blue curve, but they actually don't touch. And if I were to like zoom in really small numbers, you would see they're separated. It's just on this view, they're so close together, it can't help it, right? There aren't enough pixels on the graphing calculator for it to work. Well, I'm getting a call from Mr. Johnson. I can't answer right now, but I'm making a video. So there's again, horizontal asymptote when the degree on top is bigger than the degree on the bottom. Sorry, when they're equal, when the degrees are equal. What if I make the degrees, so let's delete the cube. Now notice the degree on top is larger than the degree on the bottom. And let's remove this one. This is where there is no horizontal asymptote. Right? If you graph this, notice it doesn't look like this graph is flattening out anywhere. Maybe I need to zoom out. If I zoom 3. Oh, look, there's a whole other piece we didn't notice, right? So notice it looks like there's a vertical asymptote. There's a vertical asymptote here. If that's at -1. Remember, -1 plus 1 makes 0 in the denominator. But it looks like the rest of the asymptote, this graph is like it's going down on both sides of the asymptote, almost like a parabola. If I zoom out one more time, yeah, we kind of see it here. See how it kind of looks like a parabola shape? So what's actually happening is I have a parabola-shaped asymptote. That's like a real thing. Oh well. So back to y equals. Change this to get rid of the negative because that's flipping the whole thing over. Back to 5, I think spreads it out a little bit more. And then let's go to like a second power. And then like I can make the graph back to zoom 6 is my favorite graph because it zooms it back to normal. Notice this graph is not flattening out again. If I were to zoom out, zoom 3, this video is getting too long. I'm almost done, I promise. Notice what's happening is there's a vertical asymptote again at -1. If I let x be, whoops, you have to hit trace. If I trace -1, y is equal to nothing. There's a vertical asymptote at -1. If I trace 1, y is 2.5. If I trace 2, I trace pi. Put pi in there for x. If x is pi, y is 11.91. Right? There are dots at every x value except -1. X cannot be -1. But notice the graph, it's not flattening out to being a horizontal asymptote, right? The graph has a diagonal asymptote, or what we call a slant asymptote. This slant asymptote, it looks like a line, right? Like it looks like y equals, I'd have to do the work to figure it out, but it would be a line that cuts in between these two. The slope of that line would be 5, so it'd be around 5x if I were to put it in, but I don't think it's exactly 5x. See, it's definitely not. Maybe 5x. So this is what we're gonna do on Wednesday when we have class next. You guys are gonna love it. I don't know, maybe a -1. This is guessing. It's probably a decimal. Oh shoot, forget it. Forget it all. When the degree on top is bigger than the degree on the bottom, there is no horizontal asymptote. And that's what this last rule is saying. Okay, so what I did here was I made some problems for you all to practice. Maybe that graph helps. So this is the way we're going to do this. Here are 8 problems. Zoomed in a little too much. What you are going to do now is pause the video and work these out. Okay, I have the answers down below. So you have to pause it because I'm going to scroll up to the answers. If you don't pause it, you're going to see all the answers. I want you to find the equations of the horizontal asymptotes to each of these 8 problems. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Find the equations of the horizontal asymptotes. See, in class, we'd have time to practice these, and then we could check them, and maybe you feel more confident. So again, you look at the top and the bottom. If you're not sure, go back in this video and pause it and look at the notes. Okay, so I'm going to move it to the answers now. So I need you to pause so you can work out these answers. And then you're going to check yourself to see if you got the horizontal asymptotes right. Okay, so 1, 2, 3, pause. Okay, so now you've worked the answers out. I can show them to you. And if you didn't work out the answers, you better rewind and pause it, cheaters. So these are the solutions to the equations of the horizontal asymptotes. Notice number 1, the degree on top is equal to the degree on the bottom. So it's a ratio of their coefficients, 3/9. And 3/9 is 1/3. So the horizontal asymptote would be y equals 1/3. Number 2, there is no horizontal asymptote because the degree on top is bigger than the degree on the bottom. Number 3, the degree of the numerator is smaller than the degree of the bottom, so it's 0. 4, the degree on top is 2. The degree on the bottom is also 2. Notice I wrote this denominator backwards, kind of weakery. So the degree is the square. It's the highest power. Okay, normally that should come first. That should come first, the highest power. But notice the denominator, I didn't do that. Tricky, tricky. And so the degree is 2 divided by -1, which is -2. What's the degree of 5? The degree on top is 2. The degree on the bottom is 3. So again, when the degree on top is less than the degree on the bottom, it's y equals 0. The horizontal asymptote is the x-axis. 6 does not have a horizontal asymptote. 7 does not have a horizontal asymptote. Again, 7 is the line y equals x. It's a linear function. The linear function goes up, up, up forever, and down, down, down forever to the left and up to the right. So it doesn't have a horizontal asymptote. No ha. And then 8. I wrote this one because my daughter's birthday is 10/4/2002. In less than a month, like 2 weeks from now, I'm gonna have an 18-year-old. It's crazy. But I also, I don't know, I was just thinking of numbers and I want it to be 10. So the degree on top and the degree on the bottom are the same. So the ratio of their coefficients is 10/1, which is 10. I wrote it this way just so you would look at this fraction and think, well, can't this be simplified or changed? And it actually cannot. This fraction does not reduce. This fraction, you don't cancel anything out here. This fraction is simplified. And it looks so much like it can't be, but it cannot be simplified. This fraction is simplified. Okay, so as I was doing these answers, I had the thought, I should have asked them. If you need to pause it now and look at these answers, you can pause it for longer. I should have asked them to find the equations of the vertical asymptotes. So here are the same 8 questions. Okay, this is what we did last Monday, the equations of the vertical asymptotes. So if you would pause the video and work out the equations of the vertical asymptotes, then we'll check them. Okay, so 1, 2, 3, pause. I wonder how many people are actually not going to pause it. They're just going to take the answers. They're just going to look at the answers and say, "Oh yeah, I would have figured that out." Okay, if you didn't, go back and figure these out. Okay, you have to make yourself practice this stuff. Some of these are kind of quirky. One thing that's true about these fractions is none of them simplify or reduce. I didn't make it so that any of these simplify. Okay, none of them simplify. What that means is there are no holes in any of these graphs. Because in order for there to be a hole in the graph, remember, you have to be able to like cancel common factors out. In order for you to cancel common factors out, there have to be factors that are the same. And these things don't factor. So there isn't any common factors that cancel out. None of these were engineered to have holes in them. Okay, but there are some vertical asymptotes here. On number 1, you set the denominator equal to 0. You add 1, divide by 9. X equals 1/9. On number 2, you set the denominator equal to 0. You add 7, divide by 2. So 7 halves. On number 3, what number makes the denominator 0? 10. So that's easier than 1 and 2. Now, number 4, you set the denominator equal to 0. And you can add x squared to their side, so it's positive x squared equals 8. And then you take the square root of both sides, which gives you a plus minus. So this is something from Algebra 2 that tends to get forgotten. You may remember the quadratic formula has the x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So the plus or minus means you have 2 answers. There are 2 numbers that make this equation true, because if I square a negative, it becomes positive. So negative square root of 8 squared is 8. And now there's also a trick to simplifying radicals that you may have forgotten, but you should not have forgotten, but maybe you did. 8 contains a factor of 4, so I can take the square root of 4 and get 2 radical 2. So you got plus or minus 2 radical 2. On number 5, kind of quirky, right? Cube to the 3rd power is cubed. So how do you solve that equation? When you set the denominator equal to 0, you subtract 9, then divide by 3. And so negative 9 divided by 3 is negative 3. That's where this number comes from. It's negative 9 divided by 3. And now to solve for x, you take a cube root. Now, when you take a cube root, that is very different than taking a square root. It's kind of like eating a Snickers bar versus eating a turd, okay? They're just totally different. So a square root, you get a plus or minus. If it's a 4th root, you get a plus or minus. If it's an even root, like 6th root, 8th root, 10th roots, you always have a plus minus, always. Because an even power, when you raise a negative number to an even power, it makes it positive. But odd powers don't work that way, right? It's okay, and it's actually even okay to put a negative under an odd root. Whereas if this up here in problem 4 were negative 8, square root of negative 8, we'd have imaginary answers, or we would say there's no vertical asymptotes, because you don't have vertical asymptotes at imaginary answers. So, but on 5, the cube root of negative 3 is the same thing as negative cube root of 3. Now, cube root of 3 is a number. It's a decimal. It's 1 point something. I don't know what it is because I need a calculator. And we need to probably talk about radicals more, because that was one of the things that Miss Squire said. The Algebra 2 classes did not cover the chapter on rational functions, which is what we're doing now. And they also didn't cover radicals. And radical function chapter is usually before rational functions. So technically, when we're doing these rational functions, you should already know this, but maybe some of you are confused by this. The cube root of a negative number is a negative number. It's not an I. It's not imaginary. And the cube root of 3 is just a weird decimal, right? The cube root of 8, I can do that one. That's 2, right? Because 2 times 2 times 2 is 8. Number 6, the vertical asymptote is x equals 0, right? When you plug 0 into that equation, you get 6 over 0, which is undefined. You always get vertical asymptotes at undefined. The last two don't have vertical asymptotes. The line y equals x is a linear function. It doesn't have any breaks in it. There aren't any vertical asymptotes for a line, right? Number 8 is an even power, right? X to the 4th plus 2002. If you set that equal to 0, you would get a negative, which means you'd have the 4th root of a negative, which is imaginary. So that means it doesn't have it. So there are no vertical asymptotes when you have an odd power. So like back to number 4, if I put a plus sign here in the denominator of 4, the answer would be no vertical asymptotes. And we saw that on the graphs a few minutes ago. We had x squared plus 1 and we had x squared minus 1. Remember, x squared plus 1 was a serpentine. It didn't have any vertical asymptotes, but x squared minus 1 had 2 vertical asymptotes, at plus and minus 1. Anyway, it all makes sense to me. I know what I'm doing. I'm going to give you some homework, okay? I'm also meant to do this. We'll see who makes it this long in the video. I just created, you see I just made this at 11:35 a.m. I did a random seating chart. So here's second period. This one came up first because I did this one second. So the front row would be Taylor, Travis, Philip, Caitlin, Deck, and Anna Humphrey and Carlos. Again, Anna and Carlos, you all would be sitting right by my desk because my desk sits up here in the classroom. I got kind of tired of like not knowing what you guys look like, and I thought, you know what? I'm going to make a seating chart with all their pictures from their sophomore year, and look at how freaking adorable you all are. Freaking cute. I tell the counselors, I don't care if you give me the dumb kids, but don't give me any ugly ones. And so notice how I have all the cutest students that are in the school. Second row, Caroline, Kara, Jack, Alex, Delaney, Virginia. Third row, Sophia, Amy, Sia, Rowan, Courtney, Sarah. Fourth row, Nick. Look, Nick, you got a little shaggy mop. See, I had no idea what Nick looked like. I had no idea what Sophia looked like till today, till she turned her camera on. Amy, I had no idea what you look like till now. There's Ben, and we have Caitlin and Emily and Drew and Soliana. And then in the last row, we'd have Carter and Zach and Isaiah and Sylvia. And I'm sure some of you guys are mad about me showing your pictures from last year. But oh well. You need to turn your cameras on in class so I can see your pictures this year. In first period, you're not getting away with it either. So first period, we got Jack in the front corner. And Cheyenne and Megan and Reese and Taylor and Jackson, you guys would be up here by my desk. Again, I did the seating chart random. You can set at Infinite Campus to do a random seating chart. Okay, I did not place any of you all in any particular place. I did, I promise. And then we have Aiden and Connor and Andrew and Ben and Harrison, Malia. Look at how cute you guys are. Isaac, freaking adorable. Brianna, how cute you are. Piper, I think I've told you before, I love the name Mary. That's my daughter's name. Beck, Lydia, Tate, Jack. Jack, your hair's got a lot longer, man. Avery, Ben, Boss. Boss, I think your hair's gotten shorter from when you had your camera on like the first week of school. You have that shaggy mop going. I dig it. I got my shaggy mop going right now. Carter. Smooth rhyme Carter. Ellie. Hi, Ellie. So you guys over here, Tate and Ellie and Lauren, you guys are in the window seats. So the wall here is where the windows are. So in the back row, we have Ryan and Brett and Mark and Maggie and Eric and Lauren. That's the last row. But I have this extra seat because I have 31 desks. Oh, my drive trash is changing. What? Go away. So Will Smaldone, your brother Q, he sat in this same row last year, first period. I had Quint, but he wasn't all the way in the back. He was one up. I had Cooper Rodriguez in the back, and then Q. So it's kind of by random. You happen to be right next to where your brother used to sit, and Lauren, your sister Megan sat way up here years ago, where Ben is now. That was Megan Ansert's seat. I had some of your all siblings I'm not sure who all has siblings in here. I had Lily Breitenstein. Ben, are you related there? and I had Robbie Kaiser, and I've had Quinn Barber, old man Quinn. Anyway, all right, I'll stop. I'm making it quit now. I'm quitting. Love you. Bye.